Chemistry is all about understanding the building blocks of our world. And transforming that understanding to catalyze discovery and invention. UC Berkeley's College of Chemistry has been doing this for 150 years. When the university was founded in 1868, one of the first 10 faculty hired was chemist Robert Fisher, making chemistry part of the university's very foundation. At that point, the field was so new that he had to go to Europe to buy equipment. 4 years later, the College of Chemistry was born.
Needless to say, a lot has changed since then. We've earned scores of Nobel and Wolf Prizes, national medals, and many more honorifics than we could name here.
Grown to house research and learning all over campus, allowing us to fold in cutting-edge areas of study.
Discovered 16 new elements, changing the periodic table again
and again
and again. The college hasn't just changed what a research university can do and be.
It's fundamentally shifted our perception of some of the most basic and most profound aspects of our world.
Before the Large Hadron Collider, the world had the cyclotron. Once Ernest Lawrence invented this first particle accelerator at Berkeley in 1929, developments at the College of Chemistry really sped up. It continues to attract talent to the university to this day. Back in the 1930s, Glenn Seaborg used it to make pioneering discoveries in nuclear medicine, like iron-59, useful in the study of hemoglobin, and iodine-131, which is still used in the treatment of thyroid disease. Then in 1941, in Gilman Hall, Seaborg and his colleagues identified the first known isotope of plutonium. He went on to share the Nobel Prize with fellow Berkeley professor Edwin McMillan and to be part of the discoveries of 9 more elements, including the only periodic table element to be named for a living person. And though many of Seaborg's contributions to chemistry originally came about as part of the US government's Manhattan Project, he was a lifelong proponent of the peaceful, productive, and ethical application of nuclear science. As an advocate for the ethical use of my own invention, I can relate to that.
World War II's demands for scaling up commercial, agricultural, and pharmaceutical production revealed a new need: more and more scientifically trained chemical engineers. Berkeley answered the call. Chemical engineering was added as a program in 1945. In 1957, it joined chemistry as the second department in the college. And it didn't take long to produce electrifying results. For example, Berkeley chemist Gilbert N. Lewis had already made foundational discoveries about lithium's electrochemical properties. In 1958, Charles Tobias took things a step further, detailing and quantifying the processes by which chemical reactions produce electricity. Shortly after, Professor John Newman developed a theory for ion transfer in electrochemical cells. These early innovations enabled the lithium battery technology that not only powers our world today, but is crucial to our global effort to electrify our automobiles and power grids with clean energy.
It's strange to think that there was a time when something as basic as photosynthesis, the process that enables all life on Earth to exist, was still a mystery. But that's how things were before Melvin Kelvin came along. Labeled Mr. Photosynthesis by Time magazine, Melvin and his team mapped the route that carbon travels through a plant during photosynthesis. The result appended was scientists previously understood about photosynthesis, showing that sunlight fuels organic compound creation not through carbon dioxide, but through chlorophyll. The impact of this discovery was huge, sparking the US Department of Energy's interest in solar energy as a source of power. And in 1961, Kelvin was awarded the Nobel Prize for his work. All of this, and he was only 34 at the time, the project started here at Berkeley.
It's hard to imagine how the last 150 years of chemistry at Berkeley could be more groundbreaking.
And the foundation that these chemists and chemical breakthroughs established are the very reason the College of Chemistry is poised to transform the future.
MOFs, or metal organic frameworks, if we're being formal, combine metal and organic ions which act as extremely porous tiny sponges that absorb and store liquids and gases. For instance, we've created a MOF that traps moisture from the atmosphere, and then when it's heated by light, releases that moisture as drinkable water. But supplying water to drought-stricken areas is just a start. MOFs can be used to capture greenhouse gases emitted from power plants or store high quantities of fuel in small containers. The potential applications are bound only by our imaginations.
What could be done if we had the power to manipulate microbes into miniature assembly lines to chemically engineer fuels, materials, or even life-saving drugs? Luckily, we here at Berkeley found out. Malaria threatens millions and kills hundreds of thousands of people a year, and large-scale production of medicine was too expensive for the countries that needed it most. So my lab genetically re-engineered a yeast with new metabolic pathways in order to more economically produce artemisinin, the most well-known and effective cure for malaria. In the last 15 years, malaria deaths have been cut in half. Once we proved synthetic biology's potential, we moved on to other pressing global concerns. The Zero Acre Farm Project is using fermentation to make new healthy oils and fats that aren't just better for your body, but eliminate deforestation for production. Next up, clean biofuels, decontaminating groundwater, and countless more ways to re-engineer nature for the good of society.
So much can be said about CRISPR's potential. The diseases it may cure, the plants we could engineer for sustainability, the risks it possesses. But we're on the cusp of seeing how scientists will wield this tool for good. Recently, the Food and Drug Administration approved a clinical trial to treat sickle cell disease using CRISPR-Cas9 to edit the mutated beta-globin gene that causes the disease and replaces it with the correct version. If we're successful, we're not only opening the door to a treatment that's accessible and affordable to patients worldwide, but also to knowing that this is really just the beginning of CRISPR's radical story here at Berkeley.
Our past and present have set a high bar, but we're aiming even higher.
We will catalyze a sustainable future, one in which chemistry and chemical engineering play a vital role in circular economies.
Quantum computing and information science,
Carbon reuse,
antibiotic resistance, and disease prevention.
and that's just the start. Our ambitious campaign, lighting the way for the next 150 years, will allow the college to continue illuminating solutions and transforming our understanding of the world.
Be a part of our bright future by helping ensure our singular tradition of excellence and our impact on the future of science and society for generations to come.